Okay, welcome to this evening's computational physics event with Dr. Andrew French. It's going to be on relativity, special relativity, and um, and there's no point in asking lots of questions about trying to explain it. Um, or the people monitoring this, I'm sure, could explain it, but I don't think they can do it within the chat. So you have to sort of get the overview for this, see what sort of things you can do in the computational side, um, and make some notes. Make some notes about the ideas, but not the detail, because if you haven't covered relativity, this is not the moment to sort of get to grips with it. It will be explained to some extent, and you can see how it can be used and illustrated. And part of the exercise is to just get that sort of overview. If you've covered a bit of relativity, that's great, but it's not a requirement. So just sort of try and sit back, make some notes, get the ideas, the sorts of things you might want to present when you do your own project, the sort of the graphs, the pictures, the sort of the way it's produced as a project. Okay, so over to you, Dr. French.
Good evening, everybody, and welcome back, or indeed welcome to the Computational Physics Challenge for the British Physics Olympiad. So tonight we're looking at special relativity. So this is a topic which obviously one of the more interesting and paradigm breaking ones of the last century. Often something that you might not discover at school, but certainly at university. So yeah, we're certainly going to follow the computational paradigm as usual tonight, but this might be something a bit new. So here we go. Just as there's some resources as usual. We have a relativity page on the Eclecticon. And if my fantastic students pops that in the chat, it's on the Eclecticon Physics Relativity. You can download this presentation and other few bits and bobs. We've also got the BPhO page here as well, with for the Physics Olympiad and the Computational Challenge, which has this special page for it. So on special relativity will also be part of the forthcoming Science by Simulation 3 book, which will also be looking at quantum physics and astrophysics too. So let's have a look at special relativity. Let's just make sure we've got that. There we are. Let's move that out of the way. Fabulous. How do I move that sort of thing? There we are. Let's have a look. How do I get rid of that? Hang on. Can I just convince? Am I still broadcasting, guys? I've not just removed the screen, have I?
No, still going.
Fantastic. Great. Right. Okay. So this is an introduction to special relativity. So this is based on a number of things. So there's a fantastic book by Swartz and McGuinness called Introducing Einstein, and it's by a company called Icon Books. So if you've ever not come across these before, they are fantastic. I don't know if I've got an example of this. I think I've got one of these. Extract it from my. There we go. So I can't quite access the Einstein book. If you can see this in the corner, this is Introducing Infinity. They're all A6 size, and they're basically cartoon books. Absolutely brilliant. So you can wage yourself for a big old tome. And I think you can get a lot more information quickly from these amazing books. And also my colleagues at Winchester College, so the kind of surreal hamster and duck, or not a duck, not a hamster concept, I can credit to the amazing and enthusiastic Mr. Douglas from Winchester College. For those of you on this call who are from this institution, you will know exactly who I'm talking about. And also Dr. Barron as well. And indeed the book Classical Mechanics by the Harvard professor, Mr. Morin. So lots of stuff into this. And of course, Mr. Einstein himself. So let's make a start. All right, so 1905 was a very, very good year for this gentleman, the patent clerk, Albert Einstein. And I'd also, so this is basically a kind of, he published in A Nail into Physics, the electrodynamics of moving bodies, one of three amazing papers, including the photoelectric effect, which he won the Nobel Prize for. And this one really is one of the key papers that sort of kick-started the modern physics revolution, of which we'd add quantum mechanics to, and eventually general relativity as well, but that wasn't for about another 10 years. And also going to credit this chap, one of the most popular physicists, Richard Feynman, who won the Nobel Prize for quantum mechanics, the quantum electrodynamics, and his amazing Feynman diagrams. But the sort of models of special relativity, I think we can kind of credit Richard Feynman for creating. And we'll sort of, you can judge for yourself whether that's explicable or not. But they're the ones which are presented in the Introducing Einstein book. So I actually I went to have a look for this paper when I was at university, and I found it in a very dusty cupboard. I'm afraid I don't speak German, but I did manage to find it after sort of searching for half an hour. I feel it should be in a nice glass cabinet somewhere. So all these amazing ideas start somewhere in perhaps a slightly obscure journal, and maybe some of your ideas may start that way. Who knows? So, okay, so we're going to start with light. So I'm going to make the bold suggestion that this is perhaps the best understood of all physical phenomena. All right. Why do I say this? Well, if you think about it, if we go beyond our solar system, places where we have scratched and sniffed and, taking physical measurements, there's no way we can actually really be in physical contact more than a few tens, maybe a few hundreds of astronomical units. Whereas we get light across the spectrum, of course, from billions of light years all over the universe. So, by looking at light, that is our window on the world, literally. So by understanding light, that is at the heart, interestingly, of relativity. So we can, for several hundred years now, we've been looking and penetrating the mysteries of light by splitting it up, by using dispersion in a prism, something like this, to see what the structure of light is. And as you probably know, we have the electromagnetic spectrum of waves all traveling at the speed of light. And solar radiation from our sun, for example, has this amazing spectrum centered around 500 nanometers. And there's a bit in the UV and there's a bit in the infrared. And in fact, that curve and analyzing it is at the heart of quantum mechanics. That's a story for another day. And we can look at the gaps in that spectrum, the absorption spectrum or the emission spectrum, and that tells us about what stars and what galaxies are made of. Okay, so basically light, I think I've said here, is the only means for us to understand the cosmos well beyond the inner solar system. So why am I mentioning light here? Well, here we go. Here's our electromagnetic spectrum. And we all know that in a vacuum, light moves at just under 3 billion meters per second. Now, that's a really interesting idea. Why does it always move at that speed? Surely if we go really fast, all right, like, half the speed of light and shine a torch, well, it should kind of appear, a bit faster depending on who's observing this, or slower. Could we catch up on a light beam? And this is the sort of thought experiment that apparently Albert Einstein was thinking about when he was a young man. And we're going to really go with that idea. So the fact that light seems to have this fixed speed is kind of strange. What does that mean? In fact, it's in a vacuum. So we'll have a little look, and this is an amazing picture. So this is looking at the center of the Milky Way. Can I just come out? Am I broadcasting okay, by the way, guys?
Yeah, all good.
Fantastic. And if you have any questions, do put them in the chat. I'll pause every few minutes and we'll deal with those. So this is looking towards the center of the Milky Way in the visible spectrum. And what we're doing is we're overlaying that the images from sensors in the X-ray and indeed the gamma ray parts of the spectrum. So we can't see those with our eyes, but we can kind of have sensors which react to light of those wavelengths. And you see an amazing kind of dipole pattern that's sort of consistent with like a little tiny antenna or something like this. But just look at the scale, 50,000 light years. So light itself takes 50,000 years to traverse this scale. Amazing stuff. Right, so light's a wave. All right, it reflects, it refracts, it diffracts. And these are some of the pioneers of this wave picture. You might have heard of Christian Huygens, 1629 to 1695, not too far off when Newton was about. You might have heard of Thomas Young's double slits. He was also very interested in Egyptology. And if Champollion hadn't beaten him to it, he might have also been credited with translating hieroglyphics. Maybe some of you might have heard of Augustin Jean Fresnel and the Fresnel zones, Fresnel lenses, very much important in for lighthouses. Foucault as well, and Physio. Now, these guys actually measured the speed of light using clockwork. So this little diagram in the corner that sort of shows you how they did it. And basically, the length there was the kind of length of the Champs-Élysées in Paris, I think. And so they bounced light off a big old mirror, and they would spin this sort of amazing piece of clockwork like a sort of strobe-like effect. So the time between the notches was the there and back time for light. So they kind of spun this up until they got sort of like some obscuration from the bounces. And that way, by measuring the speed of your clockwork, they could figure out the speed of light, which to one significant figure is about 10 to the 8 meters per second times 3. We've also things like Young's double slits, and you can see a really nice, one of my favorite experiments in the lab at school. This is one of our old benches. We've got a red light here going through a grating. So if you don't know what that is, it's basically some slits, but not just two of them. The slit spacings, I think we've got the smallest spacing is 1 millimeter divided by 600 or something like this, or 1 millimeter divided by 300. So really thin, and you've got lots of them. So the laser beam itself, maybe a few millimeters thick, covers many, many slits. And what you find is that splits up the lights. You get a diffraction pattern. So the double slit, that's what the pattern looks like. The axes are power and the bottom axis is angle. So you can kind of wrap that around a curve and you see this sort of fan-like pattern. But with the grating, the sort of gaps in between them become much, much sharper. So that's one of the effects of a grating. Really good bit of mathematics there, if you haven't yet studied that. So we know light is a wave. It exhibits these wave phenomena. Okay, and so you might also realize that light, well, certainly electricity and magnetism, light's an electromagnetic wave. Let's look at the picture at the bottom. So we interpret light moving in the Z direction, and it's transverse. Well, what are the transverse components? What are these amplitudes? Well, they're an electric and magnetic field. H is the magnetic field, by the way. I think the thing that's in, well, actually, it's not in Tesla. It's related to the thing called the flux density in Tesla. But for all intents and purposes here, they are in the same direction and proportional to each other. So magnetic field and electric field are perpendicular, transverse, both to the direction of propagation. So if you have a charge, it will move up and down. If you have a sort of magnets, it will move up and down the other way. And this propagates itself through media like glass and water, but also a vacuum. And it itself moves. All right, the disturbance itself in the electric field created by a charge like this one. Here's an electric dipole. So the red splodge represents a positive charge, and the blue splodge represents a negative charge. And we've got field lines between them. And if you have another charge that's sort of lurking around, say a positive one, the field lines tell you the direction of the force on that charge. And that's what a field is, the force per unit charge. And you can do the same with the magnetic field. So you've got a coil, like this one, a solenoid. You can plot the field lines. So this picture here is, you imagine a kind of 2D slice around this, this coil. So you imagine a kind of that coil in a piece of plastic, and we sprinkle some iron filings. They would form this pattern. Hopefully some of you have done that at school. So we can create these mathematically. And so electricity and magnetism are related. And Hans Christian Ørsted said, well, the magnetic field, or the magnetic flux density, remember that's kind of proportional to H, it forms little sort of spirals around a current carrying wire. And if we bend that into a solenoid, we get the pattern you can see here. So understanding electromagnetism has been really, again, bold bit of statement here, has gone from, mechanics pushing stuff using sort of crude machinery to the modern world. And see, there's some of the pioneers. You may have heard of lots of them, people like Faraday, Maxwell, Lorentz, Hertz, as in frequency. Marconi, you may not have heard of him, but he was basically one of the inventors of radio. And Lorentz, obviously, the Lorentz force, etc., etc. Hermann von Helmholtz coils are pairs of coils. But really probably the main person here, I would say, is probably James Clerk Maxwell, who coded all this mathematically. And there are 4 equations which describe how charges and moving charges, like currents, produce electric and magnetic fields. So these are linked. And this was known, very well known, before Einstein, the turn of the 20th century. So this is the kind of result. And what's really quite cool is that James Clerk Maxwell looked at disturbances in electric and magnetic fields, both transverse. And it turns out from the equations, the 4 equations that define these things, it turns out if you combine them together, you work out a speed of these waves. Now, this wave speed depends on constants. It doesn't depend on the source of the waves. Now, this is a bit weird. What other thing doesn't depend on that? If you go running and you throw a ball, right, I know, 10 meters per second, then the speed of the ball is your speed plus the ball speed, right? And if you're sort of watching someone running at 10 meters per second, throwing a ball at 10 meters per second, you will see the ball going at 20 meters per second, right? That just makes sense. But in this case, the speed of waves doesn't depend on any source at all. It just depends on these 2 constants. What are these constants, by the way? Well, mu naught is if you get a current carrying wire, if you remember our little picture here, and you want to work out the magnetic flux density, the thing that's in Tesla, all right, the magnetic field essentially. Basically, if you divide the current by the radius, the distance from the wire, the constant in front of it, which turns it into Tesla, is mu naught over 2 pi. All right, that's called the permeability of free space. It's a constant of the universe, same everywhere. And if we look at the forces between 2 charges, so let's just say 2 electrons of charge 1.6 times 10 to the minus 19 coulombs, and d's the distance between them, the thing that turns charge and distance into force in newtons is this constant epsilon naught. Well, 1 over 4 pi of that, but that's called the permittivity of free space. So these 2 constants are universal. We believe they're the same everywhere in the universe. And if you multiply them together and square root it and divide by 1, you get the speed of light. That's pretty cool. But it's more interesting than that because it's independent of the source speed. So the thing that's producing all waves. Now that's really weird. So Albert Einstein, maybe he's the first person, maybe not, but really thought, hang on a minute, this is very strange. I'm going to believe Maxwell is correct. What does that mean? So there we go. That's our starting point of special relativity. Okay, so here we go. Some bad humor time. This is Mystic Meg, not that kind of medium. So here we go. This is Mr. Douglas' idea. Is it light like a duck? Does it require a medium? So this is a duck creating a lovely Kelvin wedge of ripples. But for water waves, we need a medium, water. All right. And the depth of water and the surface tension that affects the waves. But a space duck in producing light, you can imagine such a thing. We don't need a medium. The vacuum is empty. So now, of course, before Michelson and Morley, it was thought, well, surely everything must have a medium. Waves must have a medium. So the medium for light waves was called the luminiferous ether, something entirely invented. And no, that is not correct. So light is not like a duck. Now, this is a little picture. Might be worth a bit more, take your time to really go through this one. But essentially, what these guys did is they had a light source and bounced off a sort of partially silvered mirror, this thing, and bouncing off some other mirror. And it's called an interferometer. So you've got the sort of mirror bouncing off this bit here and light going straight through, and their constructive interference can be looked at. I find this diagram's a bit confusing because what it really does, it relates to the Earth going around the sun. So perhaps this is a better picture to actually see in reality what happens. So this is the sort of bench they had. It was an enormous stone slab sitting on a trough of mercury in a basement somewhere in Cleveland, Ohio. They had a bigger experimental budget than we do at Wing Chul. And so what they had is lots of mirrors here. You can see it's an optical bench, half silvered mirrors and a detector. And so what they did is they looked at light bouncing off the direct route and the sort of like sideways route here. Now you'd have thought, well, there's going to be no difference here. But of course there is, because if the Earth is moving through the luminiferous ether, you should see the effect of like a river. If you were to sort of like drop a duck and going through a river, transversely or longitudinally, the speed of waves or the speed of the current in the river should be observable in the motion of the duck. All right. So as the Earth goes around the sun, at some point we're going to kind of experience a sort of drag or a gain as a result of the relative motion through the ether. Right? Remember, the orbital speed is about 30 kilometers a second. So you should see something. And in fact, you can calculate what your sort of speed would be. But what they discovered is there was absolutely no change. So regardless of the relative motion between the Earth and the Sun, all right, they could not detect any effect of some medium that would be moving at relative velocity to the Earth as it goes around the Sun. So in other words, this was a null experiment. So basically it said, did Michelson Morley observe any phase shift, any interference due to relative motion between the Earth and the ether? Well, the answer is no. Light is not like a duck. Okay, there we go. So that was, I think this duck was, I think this is a real, not photoshopped image. I think this was, I think it's in Hong Kong. This enormous duck was floated down the river. So there is no ether. Light can propagate in a vacuum. It itself moves. The electromagnetic waves propagate on their own in a vacuum at just under 3 times 10 to the 8 meters per second. Now, this is strange. Okay, so let's go back to Maxwell's discovery. So these are fundamental constants, right? They are independent of the relative speed of the wave source and indeed the receiver. So here we go. Einstein assumes Maxwell's correct. C is always the same. And he was known for his Gedanken experiments, a thought experiment, stuff that, well, maybe it's impractical to do an experiment in a lab, but we can kind of imagine how we might go about it if we had infinite money and time and space, etc. So, for example, if you were to be shaving, here's an old school shaving mirror, and if you were to somehow move close to the speed of light, or perhaps faster than the speed of light, what would happen to your reflection? Could you catch up with it? There we go. I think maybe your mirror might crack if you bumped into it, but the speed of light. But what would that mean? And this is a, although a slightly sort of playful and mad experiment, if we are going close to 3 times 10 to the 8 meters per second, let's just say we had a spacecraft that could do this, what would happen to the light beams? Could we ever catch up with them? Of course, Maxwell would say no, because it doesn't matter. If this is the formula for the speed of light, then that has no bearing, and there's nothing there that tells you how fast you're moving. It's based on fundamental constants. Now, how do we square that? So before I continue, do we have any questions for me to deal with? Am I still broadcasting? I hope I am.
All good. We're going for the questions.
Marvelous. Right. Okay. So we've had a duck. Now for a hamster. So what we're going to do, we're going to go back a little bit and look at Galileo and indeed Isaac Newton. Think about particles. Think about balls. Think about little things moving around. And as we know now, of course, we have a particle model of light as well. All right, we'll look at that in the quantum part of this course. The photoelectric effect regards, and Planck's idea, we regard the sort of energy quanta. So light is quantized, and that one-to-one interaction with electrons explains the photoelectric effect. And of course, that was understood by Albert Einstein too. So what's going on? Could we maybe think of a kind of particle model for light instead? So before we do that, let's assume a rather mad experiment of a kind of glass elevator in space where we can ignore gravity. Okay, so here's our spaceman, and he's hurling a hamster. This hamster is, is pretty much consented to being hurled around. He quite likes. He's an elastic hamster and likes this. So the idea: the hamster's hurled at speed u and bounces elastically off the wall of this glass elevator. It's the little hamster's going to bounce around like a clock, right? It's going to keep going, and so there we go. So how long does it take to travel the height of the elevator? Well, that's going to be the length divided by u. Okay, that's quite nice. We've got a hamster clock here. So, well, is light like this? So rather than a hamster, could we maybe think of a light pulse bouncing elastically off the top? Of course, we know that light has momentum as well. But just think about light reflecting. We know light reflects. We've known that for centuries. We've looked in mirrors, etc. Could this work? Let's look at the hamster model first, and then see if that then works with the light version. So here we go. This is a kind of a simplification of Professor Feynman's light clock kind of environment. I've also kind of borrowed it from Charlie and the Great Glass Elevator, which is one of my favourite books from when I was little, by Roald Dahl. You can see them all moving around. So this is my glass elevator. So what we're going to do is we're going to have our hamster bouncing from the top to the bottom like this, merrily away. But we're also going to move it sideways. Okay, so Professor Feynman is sitting in space, right, at relative velocity 0 compared to this sort of thing. And he's looking at this elevator move past him at velocity v meters per second, 90 degrees to the hamster. Okay, of course, it's an glass elevator, all right, with no refraction. Okay, so what does he see? Well, as the hamster falls, right, the glass elevator is moving at speed v. So as it goes along here, the hamster's forming this sort of diagonal line, according to Professor Feynman. You know, he can't detect that there's glass here. Glass is just to make sure the hamster doesn't, run out of air or something like this. So in delta t seconds, how long it takes the hamster to go from the top to the bottom, the glass elevator will move v delta t. Okay, so really sort of simple kinematics. So there we go. So L this way and v delta t this way. So how far has the hamster travelled? Well, we can use Pythagoras, right? There's Pythagoras. So L squared plus v squared delta t squared square rooted is the distance from there to there, right? Now, we're going to do a little bit of algebra now. If we factorize out, firstly, if we substitute for delta t, that's L over u, and then we factor out L here, well, L squared, we've got L times the square root of 1 plus v squared over u squared. So eyeball this. We're not going to do a huge amount of algebra today, but some of these things you might want to do yourself in slow time. So let this wash over you for the moment. So what's the hamster speed going from the top to the bottom? Well, it's the distance travelled divided by delta t. That's how long it takes for the hamster to go from top to bottom, right? Obviously, the hamster's clock will be the same as Professor Feynman's, right? So what is that speed? Well, it's u times this square root factor. Now, that's definitely bigger than 1, isn't it? Because regardless of whether v is bigger or less than u, we're adding a positive constant to 1. So this quantity w, the speed of going along here, must be bigger than the speed of the hamster. And that's obvious, right? Because he's going further. Now, we have a problem. Because if the hamster was like a light pulse, right, like this one, so if we replace the hamster with a light pulse, it's the same picture. But the problem is, right, the speed of light is supposed to be a constant, independent of your frame of reference. So in the kind of elevator frame, the light pulse is going from the top to the bottom at speed c, and it's going at speed w, which is c root 1 plus v squared over c squared, according to Professor Feynman. But that can't be right, all right? That is faster than c. So something's got to give, right? Literally, there's many puns in this talk. Time for a bold leap of the imagination. So something's got to be wrong. Now, what is wrong? Is it this idea of Maxwell, the speed of light? I guess most people would say, well, yeah, that's got to be the thing that's wrong. Surely intuition must rule. But Einstein couldn't find anything wrong with Maxwell's analysis. So, unfortunately, we're going to have to change our concept of both time and space. Told you it was a bold leap with imagination. So, this is how we're going to do it. Light is not like a hamster, I'm afraid. So, here we go. Here's some maths. Let's go through it nice and slowly. So, the way to square this, literally, because it's Pythagoras, is we are going to change the amount of time that passes from Professor Feynman's frame, which is the kind of T frame as we got, and the elevator frame of reference. So the dash means the time, the clock that corresponds to the light pulse in the elevator. All right. So T dash is 0 is when we start here, and T dash is L over C is how much time has elapsed when the pulse goes from the top to the bottom. All right. But in Professor Feynman's frame, V delta T, all right, is the amount of time it takes for the elevator to go from there to there, i.e. when the light pulse hits the bottom. And what we're not going to say is that delta T and delta T dash are the same. With me so far? So, what is Professor Feynman going to measure? So the speed of the pulse is the sort of Pythagorean distance. So that's L, all right? That's what Professor Feynman measures. So L squared plus V squared delta T squared square rooted, that's the distance there, divided by delta T, and that is the speed. We're going to set that to be the speed of light. So if you multiply that out, what we've got is C squared delta T squared is L squared plus V squared delta T squared, or L is C delta T times this thing, all right? 1 minus the square root of 1 minus V squared over C squared. Now, okay, let's have our bold leap of imagination. The length of our elevator is going to be the speed of light times the time difference in the elevator frame, all right? And we're not going to say that that's the same as delta T, because that leads to this problem where the speed is not the same for Professor Feynman as the light pulse. So if we set L's equal to each other, that means delta T dash, the time elapsed in the elevator frame, is delta T times this factor here, all right? So Lorentz, who I think was one of the first person to look at Maxwell's equations experimentally, analysed this too, and rather than this factor, we look at 1 over that. All right, so the Lorentz factor, which we're going to go and plot in a moment, is 1 minus V squared over C squared to the power of minus a half, or the 1 divided by the thing I'm circling at the moment. So we have our first special relativity result, and that is that the time that elapsed in the moving frame, if you like, the glass elevator, is the time elapsed in the sort of laboratory frame from its stationary relative to the elevator, divided by this gamma factor. So moving clocks run slow, all right? Why is it always run slow? Well, gamma is always going to be bigger than 1. How do we know that? Well, let's just go and plot it, all right? So this is gamma. We're going to go and plot this in MATLAB in a moment. So everything we talk about for special relativity has this gamma factor. And it's a function, if you plot it. So I'm plotting it as a function of V over C. So the speed of our elevator as a fraction of the speed of light. And if you plot that, it starts at 1. So in other words, for relatively modest speeds, a few thousand meters per second, who cares? This is not an effect that we're going to measure. And that's quite important because we don't experience special relativity in our normal working lives, all right? We don't. You may think that, when you're having fun, time goes quickly, or when you're doing a really boring task, time seems to dilate. But that's just, our perception of it. It doesn't really work that way. Your clock, unless it's wrong, goes at the same rate. However, if you were to go really fast, like, a good fraction of the speed of light, we start to see genuine time dilation. And as we get to, say, 0.8 the speed of light, it's about, 1.6. When you get to 90% the speed of light, we're now at about 3.4, and it gets closer and closer. And as you get closer and closer to the speed of light, the amount of time that elapses in the moving frame is getting towards 0. So this is immediately really interesting. So light itself, all right, moving at the speed of light, is atemporal. No time exists for light. And I think that's extraordinarily profound. Okay. So there we go. Do we have any questions so far about time dilation or anything we've looked at?
We're going through them for now.
Marvelous. So
We'll
what we're
probably
going to
have some at the end.
Okay, so we'll take a little pause and I'll show you how to plot this. So again, every time you meet something new and interesting in physics, what you want to do is, before you just keep going, embed the idea by plotting it and curling something up, making a picture, and that will really make it more memorable. So this is so again, we're not going to do something particularly sophisticated today, but this is such a nice relationship. I think we should plot it. So here we go. This is how I do it. So I'm going to do this in MATLAB. If you have some Python to hand, I'll show you how you do it. So this is a really simple MATLAB script. I'm calling this Lorentz_factor.m. Remember, in MATLAB and lots of other languages, you can't have spaces in the titles. So all I'm going to do is plot this. So I've got some, if you've never coded before, if you're new to this kind of thing, this is literally the commentary, what it's going to do. And now I'm going to do a few things. So let's just let's put some line returns to sort of go line by line what we're doing. So V over C equals lin space 0 to 0.99, comma 1,000. What does that mean? Well, I'm going to create a linearly spaced array, 1,000 elements long, between 0 and 0.99. So let's do that with a few less elements so you can see what I'm doing. So lin space, this is my command window for MATLAB, 0 to 0.99, and let's have 10. And what I'm going to do is I'm going to transpose that by going dot dash so you can see all of them. So there we go. We've got 10 elements, like I think like a column vector in Excel, something like that, 0 to 0.99, and they're spaced equally. In this case, 0.11. All right. So I could do that with, say, 7 spaces if I want. And there we go. All right. So a really useful kind of construction device. I'm now going to define my font size. And then I'm going to define gamma, which is 1 minus V over C. Okay. But I'm also going to square it. So square is hat 2. And I need a dot here because this is an array. So if I do answer dot hat squared, that squares every element of this. So maybe if I do, I don't know, x equals 1 to 10, right? And then I do x dot hat squared. Oops, wrong one. Let's go for this one. And x dot hat squared. You can see I'm squaring all those numbers here. All right, so this is an array and I'm squaring each bit. And I'm going to raise it to the power of -1/2. That's what my gamma factor is, my Lorentz factor. What am I going to do now? Well, I've got these two things. And if I hover over this point and run it, okay, so we've got V over C. If you hover over it, you can see this array. And if you like, you can make it look like a spreadsheet. There we go. We've got lots of elements. There's lots of them. And we've got gamma, which again is mostly 1 until you get quite big. All right. So, all right. So if we then get this and plot it, all right. So what I'll do, I'll keep stepping this. So we've made a plot. There we go. There's my plot. Of course, it's a piece of art at the moment. We need some axes. So if I keep stepping, the next line, I'm going to put a grid and I'm going to label it at speed V. So the bits in kind of purple mean text. So in MATLAB, this is a string of text files. So I'm going to put that in quotes. All right, I've got a few options here. So R dash just means a red line, and it's got a line width of 3. And I'm going to set the font size for my axes to be this number here, 18. So these are all the kind of parameters of my graph. And MATLAB's quite good at this. Matplotlib is the equivalent one for Python. And they will have a similar syntax, so you can control everything about your graphs. What I'm going to do, I'm also then going to print it as a PNG file. Let's just keep, let's go continue, and let's keep doing that. And what I'll end up with is something that looks a bit like this. Okay, let's make that a bit smaller. There you go. All right, so we've got a nice, really professional looking graph, high resolution. We can make all the colors different and all that sort of stuff. Fonts different if you wish, but there we go. So we can plot it, and we've got this thing that goes, starts at 1 and then gradually increases and asymptotes to infinity, but only when V over C it tends towards 1. Okay, so let's go back to our little talk. So we've got time dilation, and there we go. So if you think, is this really true? Well, actually, yes. So far, lots of experiments to be done. In 1964, as Alvaja, I think it's how you pronounce it, they fired protons into beryllium to create these things called neutral pions, and they decayed into photons. So the pions are traveling at 0.9998 C. That's pretty fast, right? And the photons are traveling not at C plus that, but at the same speed of light. So even their source is moving incredibly fast. They still produce light at the speed of light. Okay, this is like the picture here. And, you know, basically every experiment so far has passed this test. Lots of examples. Right, so I'm just going to move forward a little bit. There we go. Right, so, okay, so what about, so we looked at time. What about space? So before we do that, let's look at a little example. And plotting this example is a really good thing to do. I've written this up in Science by Sim 3, and you can download it from my website. It's called the Twins Paradox, and it starts like this. So let's have a look. We've got one twin is going to go from Earth to Alpha Centauri, our sort of nearest star that's not the sun. And it's about 4 light years away. So what's going to happen is that the sort of spacecraft's going to go from Earth, and let's say our rocket goes at a uniform speed of 4/5 the speed of light. Right? Just say we can achieve that. So what's going to happen? It's going to go to Alpha Centauri, spend a year there, and then come back again. So from the Earth's perspective, how long does that take? Well, it's going to be 4 light years, going at 4/5 the speed of light. So that's going to be 5 years. Times 2, so that's 10 years of travel and 1 year visiting, taking holiday snaps of Alpha Centauri. So 11 years, all right? But what about the astronaut? Well, the moving time, we've got to remove the 1 year from it. So the 10 years divided by gamma, plus 1, of course, is how much time has elapsed. And if you work it out, gamma is 5/3. So, if you use Pythagorean triples and that kind of thing, you get some nice numbers out of this. So the astronaut will their time will have elapsed by only 7 years. And a bit of popular culture link. I hope you like Queen, the amazing rock band. Well, they did a lesser known song called 39, which is a folk song, and it's all about relativity. All right, Brian May, of course, was a great physicist as well as one of the world's best ever guitarists. And I think the idea of the song is that the travelers go back to the nearby star or planet, and they're away for a year, but unfortunately 100 years has passed on Earth. It's a very wistful and sad song. Good tune. So this isn't quite as bad as that, but it's 7 years compared to 11. So if you had a twin on Earth, they are not the same age anymore. So, okay, you may think, great, fantastic. This helps to explain a mystery of muons. So what are muons? Well, they're kind of slightly heavier electrons. And muons are kind of created in the upper atmosphere via cosmic rays actually will sometimes decay to electrons and some neutrinos, these really tiny particles. So they have a half-life of about 2.2 microseconds, and they travel at about 98% the speed of light. Okay, so it's a good candidate for special relativity. So you can have a detector on the Earth's surface, and you can maybe fly one up into the upper atmosphere. So how long should it take for a muon to go through 10 kilometers? Well, that's 10 kilometers divided by the speed. That's about 34 microseconds. So that's 15.5 half-lives, right? So if you were to look at a detector on the upper atmosphere and one near the surface, you got 15.5 half-lives. So we divide the muon flux by 2 to the power of 15.5, about a factor of 45,000, and that's what we should get on Earth, right? So in 15.5 half-lives, right, not much, 1/45,000th of the amount of muons in the upper atmosphere should end up on the Earth's surface, right? But that's not what we measure. It's more like an eighth. So how on earth is this right? This is a mystery. So we can explain this by time dilation. So what we do is we say, okay, we've got the moving frame and the lab frame. So delta T dash is delta T over gamma. So what do we need to do? So the muon's moving clock runs slow. So it's not 2.2 microseconds, but 2.2 multiplied by the gamma factor, which in this case is about 5. All right. So in this case, the half-life that we experience, the lab frame, is the muon's half-life times gamma. So you've got to be careful with which one we're talking about here. And so delta T, the thing that we would put in our power here, is 11.1 microseconds. So from the muon's perspective, it's 2.2. From our perspective, it's 11.1. And so minus 34 over 11.1 is about 2 to the minus 3, or about a factor of 8. So that's pretty much agrees with what we see. Great, fantastic, you may think. Mystery solved. But there's a problem. Does anybody know what the problem is with this multi-perspective system of muons and lab? What's the flaw in this ointment? Would anyone like to put that into the chat?
We got length.
Right. So, okay. Well, hang on a minute. What about the muons looking at the detector? Surely that's coming towards the muon at, what is it, 0.98% the speed of light. So shouldn't it dilate both ways? Isn't that a paradox? So there we go. So surely the muon will experience a half-life of 2.2 microseconds. Don't we have a paradox? And the answer is, from the muon's perspective, it doesn't travel 10 kilometers. Instead, it travels about 2 kilometers. So how does this work? All right. So we're gonna sort of conclude this introduction to special relativity by having a look at length contraction. There are actually several other parts, but that would require a bit of a longer course. There are actually 3 elements to special relativity: time dilation, length contraction, and the really weird one, which is loss of simultaneity. And actually, you need to do all 3 to explain special relativistic effects in general. They're put together something called the Lorentz transform. And if you're interested in that, do download these slides, because that will be a sort of where you would go next. Lots of opportunities for projects, etc. So let's just have a little look at how we can prove this result. So length contraction is the length of the moving object. This is the length at rest, as it were, and then we're going to divide it, just like time dilation, by the same gamma factor. So I think we'll quite time for the poet interlude, but we'll have a little look. So here we go. This is Mr. Wonka's glass elevator. I don't know why it's Mount Wonka. I think I'm missing an R there. So we have a slightly different situation. So what we're going to do is, rather than the light pulse going down this way, we're going to have the light pulse moving in the direction that the light is moving, just like the muon. So we're going to have a little torch, which is making a pulse, and it's going to bounce off the mirror and come back. All right. So in Professor Feynman's frame, we're going to look at this one. All right. So in our reference frame of Mr. Wonka's glass elevator, all right, we're going to say its width is L. All right, and its time is going to be 2L over the speed of light. All right, it's a light speed, and that's the there and back time. Right. Now we're going to have a look at the situation as viewed by Professor Feynman. Now what he's doing is the light pulse is happening, but the whole thing is moving at speed v. And remember, this elevator is transparent. So how long is it going to take? Well, this is what I recommend. So what we do is we look at the total distance traveled by the light. All right, so C delta T, source to mirror, that's the total distance traveled. What is that going to be? It's going to be the width of the elevator as measured by Professor Feynman, plus the distance the mirror has moved in that time. So V delta T SM. All right. Now, the reason I do this is that often in textbooks, you'll have the thing I'm circling here straight away, which I must admit used to confuse me no end at university. So I think sometimes you just need an extra bit to start off with. And in that way, it's defined kind of implicitly, because delta T SM appears on both sides. But so let's just reiterate it. This is the distance traveled by the light in times, the time it takes to go from the source to the mirror. And that's the length of the width of my elevator plus the extra distance that the elevator is moving. So there we go. We can work out in Professor Feynman's frame the time from source to mirror. Now, of course, it's then going to bounce off the mirror and come back. All right. And it's going to go a bit less this time because obviously, the source is going to be going towards the light. So delta T mirror to source is L over C plus V in this case. If you factor out the TMS, you can kind of see that algebraically. So what we can do is we can relate these 2 times. So if we put that together, here we go. So there's the total there and back time. And if we do a bit of fraction action, a bit of combining these things together, hopefully you can see there's a sort of difference of 2 squares here. And what we end up doing is 2L over C times gamma squared. Remember our gamma factor. All right. Now, from the time dilation result, all right, so delta T dash, this one, which is delta T over gamma, all right, and we know delta T dash is 2L, big L, not this one, and this is the Professor Feynman's frame. So what we can do is we can replace the times with this one here. So delta T dash is this from time dilation, and delta T dash is 2L over C. So what I can do is I can cancel out one of those gamma factors. So 2L over C, the time experienced in this frame here, the mirror, the sort of elevator frame, I'm equating that to the time experienced by Professor Feynman, right, which is this one here. And by time dilation, And what I'm doing is I'm using delta t is this one. So I cancel one of the gammas, I can cancel the 2's, cancel the c's, and I end up with my my length contraction result. So moving clocks run slow, and length contracts relative if it's moving in the same direction. So if I'm moving this direction here, if I'm looking at some sort of elevator, I will sort of see it getting squished. You can see my spaceman getting thinner and thinner and thinner, the faster and faster it goes. So this is fundamentally weird, but seems to be a fact of the universe. All right. And you can put this all together to do some really interesting stuff. So there we go. I'm just going to think that let's just pause there briefly. Does anyone have any questions? Because there's a bit more algebra on this page. The main facts are this one I'm cycling, and of course our time dilation. Does anyone have any queries about anything that we've experienced so far?
Yeah, all good. A bunch of questions. We're getting there.
Do I need to answer any?
Okay, let me quickly read through. Yeah, we have seen this quite a bit. So when I'm moving, is the distance itself contracting?
When I'm moving, right? Okay, so I suppose in terms of the muon, right? So the muon experiences, so from the muon's perspective, the detector's moving towards it. If we just go back to our muon here we go. So from the muon's perspective, the Earth's surface is coming towards it, right? At 0.98 times the speed of light. So in other words, the muon experiences the 10 kilometer space to be Lorentz contracted to about 2 kilometers, because our gamma factor is about 5. All right, from the detector's perspective, all right, the muon travels 10 kilometers, but the half-life is time dilated. So it all works out. So it depends on this is the relative of relativity, right? So you're not saying there's some absolute well, be careful about saying that, but there is relative motion between two frames of reference, but we have to be really careful, or more careful if we go very fast, about what we mean by space and time relative to those frames. And essentially what we're building up towards is the transformation of x, y, z, and t, 4 dimensions, as it were, from one reference frame to another. Okay, and that mathematically, when you put this all together, it's called the Lorentz transform. Okay, anything else? Right, well, I'm going to I'll gloss over this a little, because it's basically the same kind of concept as Lorentz of the length contraction. But this is the weirdest effect entirely. And I must admit, I find a lot in several books, this is the more confusing one. So this is sort of, I'm going to sort of say I've borrowed Professor Feynman's idea. I can't remember if this is me or a classic one, but this is how I like to do it. And so what you do is you say, okay, we could take the same elevator, but instead of a light pulse going from left to right, we kind of have an explosion, a sort of, we let off a little firecracker in the middle. And so it's bouncing, one goes one way and one goes the other. And what we do is we define 2 events. Okay, so in the sort of frame of the elevator, obviously the light pulse will hit this mirror and this mirror here at the same time. Okay, because it goes the same distance, half L. Right, that just makes sense, doesn't it? But what does Professor Feynman see? Remember, this whole thing is moving from left to right. So what we do is the same thing as we did before. So C delta T R, right? That's when the pulse hits the right one. The elevator itself has moved V delta TR. All right, so we have this expression, and we can work out the time it takes to go to the left one. No bouncing now. Now, rather than adding those things together, what we're going to do is see what the difference of those things are. All right. So in other words, that delta TR, the time it takes to get from the middle to here, according to Professor Feynman, and delta TL, the time it takes to get from the middle to the left, according to Professor Feynman, those things you can clearly see are not the same. And if you work out the difference and do a bit of algebra, what you end up with is something that depends on gamma squared. So what you end up with is that the time error, if you like, or the loss of simultaneity, right? Because this frame, these 2 events happen at the same time. Professor Feynman's frame, they don't. Is gamma VL over c squared. All right. And so in other words, the clocks don't just run slow and lengths contract, but clocks go out of sync. Now, that is just weird. That just doesn't happen in our world unless you deliberately not set your clock right. But this is something that happens. And so you've got to combine all three effects, loss of simultaneity, length contraction, time dilation, to work out the transformations of space and time, as long as we're moving at constant speed. All right, so that, in a nutshell, is special relativity. So before we go, we've got a few minutes left. I'll just show you some of the kind of simulations you can do. I will gloss over the twins paradox. Let's have a little look. I'm just going to skip ahead for the moment. Actually, I think with this, I'll just show a picture. All right, this is worth going through in slow time. But basically, the twins paradox is, well, if you've got two twins going from Alpha Centauri and back, surely from one's perspective, the guy who comes back from Alpha Centauri will be younger. But then from Alpha Centauri's perspective, surely the Earth has just moved, away and then towards the astronaut. So from his or her perspective, the other twin must be younger. So who's correct? And it turns out what you have to do is you have to kind of work it all through, and the loss of simultaneity is the key. So what I've done is I've plotted the spacecraft time, T dash, and the Earth time from both perspectives. So the red line here is the spacecraft from the Earth, and the blue line is the Earth from the spacecraft. And they end up as the same kind of difference. So that's the Earth time and that's the spacecraft time. So you get the right result, but the curves are different. And what happens, those big jumps, those big vertical jumps, are to do with the fact that by changing reference frame, so in other words, rather than you're going towards Alpha Centauri, you have to change direction, you end up with a big shift in time, and that resolves the paradox. All right. Other versions of that resolution are saying, well, in order to change direction, you've got to accelerate. And acceleration means general relativity, means so there's lots of ways you can think about this. But without doing anything more complicated, the loss of simultaneity will actually resolve the paradox. And this is what we've got, a kind of time, or a space-time diagram, which is the distance versus the various times. So let's look at the Earth from the spacecraft. Actually, look at the spacecraft from the Earth. That might be the easiest one to start off with. So that's 11 years, right? And it goes 4 light years away. It waits for a year and comes back. And the Earth from the spacecraft, that takes a bit less time. So you can see the time dilation directly here. You can see once it's from its perspective, it doesn't travel 4 light years. The distance from the spacecraft's perspective is about 2.3 and a bit light years away. Okay, so all of these things are kind of work. And if you put all the relativistic kind of ideas into a little computer program and plot it and make these kind of graphs, I think that's a nice little project to do. Okay, so I think I'm going to stop there because there's loads of other things you can talk about, like momentum, energy, Doppler shift, velocity transformations, all sorts of things. But I think that will be a course for another day. So I think time dilation, length contraction, loss of simultaneity, that's really the guts of special relativity. So I hope that's been inspiration to some of you, and do have a think about that. And even if it's just plotting the Lorentz factor, but I really recommend having a go at the twins paradox and maybe trying to plot these graphs and see if you can understand the figures that you make. I think that will be certainly help me trying to get my head around this crazy but true idea. Okay, I think that is enough, unless there's other questions you want me to deal with. Any more questions?
I guess people are asking what happens when you go at the speed of light. So all of these equations when gamma goes to infinity and so on.
Well, I mean, I think that's we could certainly answer that, because basically time dilation is infinite. All right, so no time elapsed. In fact, if you look at the let's look at our time dilation equation. There we go. So well, actually, we could look at both. So if you look at time dilation, right, if gamma is infinite, then delta t dash is 0. So your moving frame, no time elapses. Okay. So if you think of the extreme, if you were to go 0.9999999 times the speed of light to Alpha Centauri, so you get there very quickly, billions of years could elapse on Earth. And that's kind of sad, wistful thing is that the faster you go, closer you go to the speed of light, when you come back, there'll be nobody to talk to you. Maybe the Earth will be gone, all right? Which is which is kind of if it's 100 years compared to a year, a gamma factor of 100. That's the sort of spoiler alert. That's the kind of basis of the Queen's 39 song. You can also think about it as length contraction as well, because you look at our length contraction idea. Here we go. If you go near the speed of light, gamma tends to infinity, then the length of your moving object tends to 0. Okay, so in other words, if you're going incredibly fast, Alpha Centauri is really close. It doesn't seem to be any distance at all. So that all both hangs together. But again, the problem is that you can't really tell anyone about it. So the bigger your Lorentz factor, the bigger the time dilation, and that sort of messes up your journey really. Well, that makes your journey okay, but messes up the people you've left behind because they may not exist anymore. So there we go. The universe is intrinsically wistful. Any more questions? Well, I think we're at 9 o'clock. So in that case, I will not be with you next week, but we are fantastic students. So we're going to get to all the lovely people who've been sending you messages and answer your queries. We'll be doing a introducing Python course next week. So that could be all sorts of things. So do come armed with some questions, and I will see you in about 2 weeks' time. Thank you very much indeed. Let's just go back to the screen, and there we go.